Welcome back to example number 2. We were looking at some interval of convergence, actually radius of convergence problems for infinite power series. So the idea here is that we have a infinite series that's not defined by terms that are numbers that I'm adding infinitely, but rather terms that have x. However, with certain x values, this power series will converge. And so we're trying to see what is the set of x values where the power series will converge. And so we said one way we can do that is by using the ratio test, because the ratio test gives us a way to determine the convergence of an infinite series. So we're going to take the limit as n approaches infinity of, we're going to take the x plus 1 term. The x plus 1 term would look like this. And we're going to divide it by the nth term. And the nth term is the term of the formula of the series. And we're going to take the absolute value. What are we looking for? In order to converge, it has to be less than 1. So I'm going to take the limit, and I'm going to see if the limit of this is less than 1. Well, I can reduce this a little bit, right? I can reduce the 3's for sure. Not only that, in the numerator, remember this, n plus 1 means I'm taking x minus 2 to the nth times x minus 2 to the 1. So the x minus 2 to the nth will cancel out with this, and just like the 3 will cancel out with that. And so I'm left with x minus 2 to the 1. Now, when I say cancel, I really mean reduce, right? 3 divided by 3 is 1. X minus 2 to the n divided by x minus 2 to the n is 1. So we reduce it. It doesn't really cancel, but it disappears, if you will. And I'm left with this. But I'm taking the limit as n approaches infinity, but I don't see an n. So therefore, the limit is just this. And I want it to be less than 1. If it's less than 1, then I know that my series will converge. Well, now I need to solve this absolute value expression. And the absolute value, we can take away the absolute value by rewriting it as this. And then we can add 2 on both sides. And when I do, I'm left with this. Now, if you think of the picture that this is creating, it's saying from positive 1 to positive 3 in this window, any of these values, any of these x values, will cause that power series to converge. Now, if you look carefully, the halfway point is the center. And if we had identified it at the beginning, remember, using this, I can figure out that the center is 2. So if the center is 2, I know that there's a symmetrical width to go this way and width to go this way. And that width we call the radius, and the radius is 1. So from the center, I have a radius 1 that will produce, and it could go to the right or it could go to the left, but any of these values between 1 and 3 will produce a convergent power series, any of these x values. So what am I looking at? I'm looking at x values that make the original power series converge, and so therefore r equals 1 in this case. Why did r equal 0 in the previous case? Well, it only converged at the center point. It only converged at 0. It didn't go out anywhere else. So therefore the radius, well, there was no radius. It just stayed there, and the radius would be 0. Not because this number is 0, but because it didn't go out any. There were no endpoints to this interval on letter A, but letter B does. We now know that this power series will converge if I choose any numbers between 1 and 3. I know, and I'm guaranteed for that to happen. Okay, we'll do another quick one, and then we're going to extend the idea of radius of convergence into interval of convergence. What are the actual values? Because if you've noticed, we haven't really talked about the fact that this interval has endpoints. We'll get to that here in a little bit. Okay, let's see. Can we figure this out? Well, I need to take the limit as n approaches infinity of the absolute value of negative 1 to the n plus 1 times x to the 2, n plus 1 plus 1 divided by 2 times n plus 1 plus 1 factorial. And I need to divide this by the original function or the original expression. But this is a fraction, and whenever I divide fractions, I really just multiply by their reciprocals. I think I have this done. Okay. Now remember, I want this limit to be less than 1 in order for the series to converge, because the ratio test says if I take the limit of the n plus 1th term divided by the nth term, it has to be less than 1 for it to converge. Well, I can simplify some things. Like here, this is 2n plus 2 plus 1. So in reality, I believe it's just 2n plus 3. And this, similarly, is 2n plus 2 plus 1. So this is just 2n plus 3. And I can rewrite this as 2 to the n times, x to the 2n times x to the 3. And I can rewrite this as x to the 2n times x to the 1. And what else can I do? Oh, this can also be split up into negative 1 to the n times negative 1. I'll sneak a negative 1 in there. Can I reduce anything? Well, yes, I can reduce this and this. I can reduce this and this. I'm still left with a negative. And even here, remember that 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 and forever. So therefore, these are going to reduce out. So what am I left with? The limit as n approaches infinity of negative x to the third in the numerator divided by 2n plus 3. Oh, I just noticed something. Times 2n plus 2. I just noticed I still had an x here. I can reduce this x with 1 from the numerator, and it becomes that. And I want to see where that is less than 1. So for what x values will this limit be less than 1? Well, if I look at the limit does not affect the negative x squared. So I can split it up and say this is really the limit of everything with an n, 2n plus 2, times the limit as n approaches infinity of everything that's not n. And I want to see when that's less than 1. But the limit of this, as n approaches infinity, this fraction will go to 0. So this whole limit becomes 0 times this limit, which is really just the absolute value of negative x squared, is really going to just become 0. And so then the question becomes, when is 0 less than 0? When is 0 less than 1? Always. It's always. So therefore, this radius of convergence is going to be infinity because I can choose any x value and substitute it into this series, and I will have convergence. I am guaranteed the convergence of this power series for any x value, because any x value I substitute and I do the ratio test, it's always going to be 0 less than 1, and therefore it's always going to be convergent. So my radius is infinity. So here I have 3 different cases. Case number C here, or problem C, says the power series is convergent for all real numbers, right? So for my radius goes on forever. Whereas number A here tells me that the radius is 0 because there's only one point. It doesn't stretch out. And letter B says the radius equals some integer, or some number, I guess, some value, because it's a window around the center point. And so when I come back over here, remember, R was the radius of convergence. It's either 0 if there's only one point, or infinity if it's for all x values, or it's a value, a number, because it is surrounding the center point. This is how we figure out the radius of convergence. In the next video, we'll talk about the interval of convergence and actually figure out what happens at the endpoints if it's a situation like letter B? What happens at the endpoints? Because all we did was found out that any point in between the endpoints, it will converge. But what about the endpoints? That happens in the next video.